Hello, everybody. Welcome back to the Origins seminar. Today's speaker is going to be Jamila Pegues. Before I introduce her, I just want to quickly remind everyone to please hold your questions until the end of the talk. If you have a burning clarification question that just can't wait, you can put that into the chat and then one of the organizers will ask it to the speaker. All right, so today, we are very pleased to have Jamila Pegues from Harvard University. Jamila got her bachelor's from Princeton University in astrophysical sciences, and she is currently a graduate student at the CfA working with Karin Oberg on protoplanetary disk chemistry, which I'm so excited to hear from you today. So Jamila, the floor is yours.
All right, hello. Let me start my own timer really quickly here. All right, yeah, thank you so much for that introduction. Hello, everyone. My name is Jamila Pegues. I am a fifth-year graduate student at Harvard University, where again, I study astronomy and also some computer sciencey things. Fun fact, I'm actually graduating in the spring. So I'm sort of in the midst of the really exciting, but also slightly terrifying period of applying to postdocs and things. So I'm actually really grateful for this chance to kind of step away from all of that and actually share with you all some of the work that I've been doing for my PhD thesis, which has been to characterize young cool M stars and their planet-forming disks. Okay, so before we keep going, quick caveat. I got sick several months ago and my voice still has not recovered. So I will be drinking a lot of water and you'll hear my voice crack in really weird places. So just bear with me and do let me know if you have trouble hearing me at all. Okay. Great, so with that aside, let us get started. Okay, so protoplanetary disks are these lovely disks of dust and gas orbiting young stars out in space. And here I've put together this very cartoonish illustration of what the cross-section of a disk may look like. So on the left, we have our lovely star, and on the right, we have the cross-section of our disk, where in the atmosphere, we have gas that is very hot because it's directly irradiated by the central star. And then towards the midplane, the material is a lot colder and denser. And you actually have certain molecules that will freeze out in the form of ices onto the surfaces of your disk grains. Okay, now I am particularly interested in disks around M stars. And that's because M stars are not only the most common stars in the local galaxy, they are also statistically likely to host planetary systems. So if we study disks around M stars, we're essentially studying the precursors to the most common planetary systems in our local galaxy, which is pretty cool, right? Now, disks are actually quite useful resources for learning about these systems. For one, you can actually use their rotation to precisely measure the stellar masses of the central star. And that's really important because stellar mass is actually a primary property for determining or mapping out stellar evolution. So to understand these stars, you really need to understand their masses. Now, disks are also really useful because they're full of interesting chemistry. So you've got small organic molecules, you've got large organic molecules, and you've got a lot of carbon monoxide, aka CO. So remember, planets are forming from these disks, right? So if we study the chemistry that's in these disks, we're essentially studying the chemistry that participates in the most common forms of planet formation in our local galaxy. So I say all that to say, that basically disks are really cool, and we should definitely study them around, in particular, these cool M stars. Okay. All right, so the goal of this seminar today is essentially to do the two things that I just talked about. We're going to start by sort of exploring this sample of 5 protoplanetary disks around M stars that was observed with ALMA. And then we're going to use that sample to dynamically measure the stellar masses at the center of those disks as we're able to. And then we're actually going to survey the disk chemistry across the entire sample. Okay. So let's start by looking at the sample. And down here, I'm showing a very pretty picture of ALMA, which is the interferometer that is the source of these, I don't know if you've seen all the really great high resolution surveys and whatnot of disks lately, but it's all thanks to the amazing power of ALMA. So thank you, ALMA. Okay, so as I said, there are a total of 5 disks in our sample, and I've summarized their stellar characteristics here. So basically they're pretty young, pretty dim, and pretty low estimated masses. Now here I'm showing the dust continuum for those 5 different disks. So each subpanel is for a different disk. And as you can see, the dust continuum appears to be pretty smooth at this resolution. So we don't see any, interesting gaps or holes or rings or anything like that. Everything just appears to be smooth at this resolution. Now, the first question we wanted to answer with this sample was, do we detect any interesting chemistry towards disks around these low mass M stars? And the answer, thankfully, is yes. Yes, we do. So here I'm showing spectra of different molecules for the 5 disks in the sample. We have each column corresponds to a different disk, and then each row corresponds to a different molecule, in this case, the CO isotopologues, so 12CO, 13CO, and C18. So we detect CO towards all 5 disks, and we also detect C2H and HCN towards all 5 disks, as well as DCN and H2CO towards a smaller subset. So what's interesting about this chemistry is that we detect the same interesting chemistry towards disks around solar type stars. And another thing that's interesting, or really exciting, I guess, is that we have all these detections because it means that I have, wonderful data to work with as a part of my PhD thesis. So that's pretty great in its own right. All right, so let's start by using the simplest molecule, CO, to actually measure the dynamical masses, the dynamical stellar masses, or dynamically measure the stellar masses at the center of these disks. So here again, I'm showing the CO emission as observed towards all 5 disks. So again, each column is for a different disk, and then each row is for a different CO isotopologue. Okay. Now, to do this measurement, you need observations that are pretty pristine. Basically, you want to be able to resolve this double peak structure because that means you're resolving the underlying Keplerian structure. Let me try to drink water without doing anything embarrassing. Hold on. Okay, that's better. Yeah, so we need to be able to resolve that nice double peak structure because it means we're getting a good handle on the underlying Keplerian rotation of the disk. So that means, unfortunately, that C18O is a little too faint. It's a little too noisy to really get that pretty sort of double peak structure that we're going for. So we're going to toss those observations out. Also, unfortunately, we don't actually, so for 2 disks in the sample, the ones that are all the way to the right, both of those disks are cloud contaminated, which means there are some pesky clouds in the way that are really preventing us from distinguishing what the cloud is doing from the underlying disk rotation, or of the disk. Yeah. So we have to toss those out too. But hey, we still have very nice 12CO and 13CO observations towards 3 of the disks. And as we'll see over the next few slides, that's actually plenty to do some really interesting investigations into dynamical masses. Okay, so how are we going to actually measure these dynamical masses? Well, we'll do that using this code called Jockey, which is so exciting, it deserves an exclamation point. It's pretty neat. They actually have their own cool logo, which I've put up to the top right. You can go check them out on GitHub if you're interested. Yeah, so how does Jockey work? Well, say we have our disk, which I really enjoy making cartoonish illustrations, as you can probably tell by now. So here's a cartoonish illustration of our star surrounded by this orbiting, rotating disk of a disk of CO. Right? And because this is an observation, and because the data is not as pretty as it is in theory, we have pretty noisy emission, which I've described using these raggedy edges, basically. Okay. So what we want to do is actually put together a disk model that best reproduces the data, right? And this disk model depends on some parameters, but the one that we really care about here is the stellar mass, M substar here. So what we do is we vary our pretty disk model until it best matches the CO data. And that's exactly what we do with this Jockey. And once we have this best fitting model, we have the best fitting parameters, which in turn yields this dynamical estimate of the stellar mass. Okay, so yeah, we do that with this Jockey. And here I'm sort of summarizing the results that we get for our 3 disks from our sample. So the first column shows the data, which as you can see is kind of noisy. In the second column, we have the model, which is much more pristine. The third column is the residuals, which is the difference between the data and the model. And finally, the fourth column overlays spectra from the first 3 columns. And then each row shows you the 12CO or 13CO estimate for each of those disks. And if you just kind of glance over these different results, you see that, hey, we do a pretty, this Jockey does a pretty good job of recovering this underlying disk structure, despite, even in cases when it's kind of noisy. Okay. Now, what's really, particularly great about using or doing this with both 12CO and 13CO is that we actually get independent measurements or independent dynamical measurements of the stellar mass, which we can then use to check each other, right? To make sure that we're actually, getting the correct results. And that's exactly what we're doing in this plot here. So along the x-axis, I'm showing the 3 different disks, and then the y-axis shows the stellar mass that we've estimated. Each of the dark purple large diamonds are the 12 CO independent measurements, and then the pale blue diamonds, the smaller ones, are the 13 CO measurements. So for 2 disks, we can see, we see that our 12 CO and 13 CO estimates are consistent with each other, which is pretty great. Now you'll notice that our 3rd disk is a little lonely. We only have the one independent measurement for J1100, and the constraints are quite large, or the uncertainties are quite large. And that's because this particular disk has a pretty low inclination angle. And it just so happens that based on how the stellar mass and the inclination angle are related, if you have lower inclination angles, you end up with higher uncertainties in the stellar mass. And so I can actually show you, if you remember from this plot, this is J1100 down here, which is almost face on, which gives us this beautiful view of the data, but that actually works against us when we're trying to estimate the stellar mass. So, you do what you can with the data that you have. Yeah, so even though, we still have, great measurements of the dynamical masses for our sample. Okay. Now the next question we want to ask is, well, what would we have gotten if we had used, standard stellar evolutionary models to try to predict these stellar masses? So stellar evolutionary models are pretty common. They're used to predict the stellar masses for a particular star, given some observations of that star. So maybe you might take the stellar luminosity of a star that you've observed, stellar effective temperature, put that into your model, and the model will spit back out to you a prediction of the stellar mass. And it's important that the stellar evolutionary models give you correct predictions, because then people will go on to use those to do interesting statistical studies of like star forming populations and things like that, right? Star populations and stuff. So you want the predictions to be accurate. So yeah, so how do stellar evolutionary models compare to our dynamical mass measurements? Well, the answer is unfortunately pretty poorly. So here I'm showing now with these gray circles, the stellar evolutionary model predictions for each of those disks. And as you can see, for 2 of the 3 disks, our dynamical mass measurements exceed even the uncertainties provided by the stellar evolutionary models. And this underprediction is consistent with what has been seen in previous works. So there was this really neat and really convenient compilation basically done by Simon et al. 2019, where basically they pulled together all these dynamical mass measurements done for all these stars and added some of their own and put it all in this nice clean paper. And so I've extracted from that sample all of their disks from the Taurus region, which had stellar evolution or standard fiducial stellar evolutionary model predictions less than or equal to 0.5 solar masses. And I'm comparing that to our own work in this plot here, where along the x-axis we have the stellar evolutionary model prediction, the fiducial stellar evolutionary model prediction, and the y-axis gives the dynamical mass estimate. Okay. Now each of the dark stars are the values from our work, while the pale purple pluses are the works from Simon et al. 2019. Now, I've drawn these lines to help guide the eye to different ratios between the dynamical mass and the stellar evolutionary model predictions. And ideally, we will want all of these points to lie on this black line, which would mean that the predictions are equal to our dynamical mass measurements. But instead, we see all of these points are clustered more on like showing that the points are underpredicted by factors of like 1.25 all the way up to 2, right? So basically this shows that these fiducial stellar evolutionary models are not doing a super great job of predicting the masses for these low mass stars. It's not ideal. So we need to do something a bit more complicated. Okay. So let's try stellar evolutionary models with star pods. So there was this really neat code released earlier this year called the SPOTS code, very aptly named, which basically presents these stellar evolutionary models with varying fractional star spot coverage. And that acts as a proxy for varying magnetic activity. And I'm sort of depicting that with some really not to scale images, or cartoon illustrations of stars with increasing fractional star spot coverage. But don't sue me on this. I realize maybe it's possible that some, star people in the audience are twitching, letting their eyes twitch at this, but it's just for illustration. Okay, so yeah, so we can use these stellar evolutionary models as a proxy for sort of exploring how variations in magnetic activity could maybe help improve predictions for these models for our sample. And here I'm showing the results of that study with this really fun plot. So the x-axis basically shows the progression in star spot coverage. So as you move to the right, you increase your fractional star spot coverage for your model. And the y-axis shows the dynamical mass relative to the stellar evolutionary model prediction. Each of these tracks basically, or each of these paths, follows one of the 3 stars in our sample. Okay. And I've highlighted in particular this black line, where basically that's the point, or the line at which the dynamical mass is equal to the stellar evolutionary model prediction. Okay. So wherever these paths cross this line, that points to the most interpolated optimal value for the fractional star spot coverage, this F spot parameter. Okay. Now looking at this plot, we can sort of take away 2 major things. First, we see that all of these tracks do intercept this magical black line, right? Which means that there is a model that exists that can actually reproduce the dynamical masses that we measured. Okay. Now, point number 2, we see that each of these tracks or paths do not intercept the black line at the same point, right? Or the same place. And that means that these different stars actually require different fractionals, basically different amounts of varying magnetic activity to actually reproduce the dynamical masses. So this raises up, an interesting question. Can we somehow use stellar characteristics to predict the optimal, F spot value, right? Because if we could do that, then we could, take our stellar luminosity, take our stellar effective temperature, use those to determine the optimal F spot value, and then we would actually have the model that best predicts the dynamical masses, even in cases where we're unable to actually measure that dynamical mass itself. Okay. And so we sort of investigated that by combining our sample with the disks from Simon et al. 2019, where we basically ran these star spots models, not only for our disks, but also for those disks extracted from that compilation. So here, each of the gray squares are those disks from Simon et al. 2019. And then the 3 circles are the disks from our own work. And so you can see, the error bars are pretty large, and there's this outlier, which is just kind of over here. It's unclear why. But we do see, something like suggestive possible trend on stellar effective temperature shown along the x-axis here. Oh, and also, I don't think I mentioned that the best optimal value is shown along the y-axis. There you go. So yeah, we see the suggestive trend. We're not going to do anything more quantitative because, again, these error bars are pretty large and we have this outlier. But this is certainly a call for future work, right? Because if we can have a much larger sample of these dynamical masses measured towards many more low mass M stars, then we could actually see or not see how this particular, how this value of F spot, how this varying magnetic activity can really serve to predict the stellar masses correctly in these models. Okay. So yeah, that's, even with just 3 disks, we learned quite a lot. So just imagine how much we can learn when we take a look at the chemistry. I'm going to take a quick drink of water though. And then we'll keep going. Okay. All right, so yeah, back to the chemistry. So if you remember, there were 5 total disks in our sample, where we're definitely switching gears here and going back to the original sample. And we had, a total of 5. And again, they were pretty young, pretty dim. And we now know that they cover a larger stellar mass bracket than was previously predicted by the stellar evolutionary models. Okay, and again, here's the disk continuum, which appears to be pretty smooth at this resolution. Okay, so when we look at the chemistry across our entire sample, we find a pretty diverse variety of morphologies, or I suppose shapes of the emission that we observe. And for example, let's take a look at J1100, which if you remember, J1100 was the one that gave us a little bit of trouble before because it was too face on to get a really precise estimate of the stellar mass. But here now, because J1100 is so face on, we actually get these beautiful views into the disk chemistry. So there you go. So yeah, so I'm showing the a subset of molecules observed towards J1100. So 13CO all the way on the left, all the way to H2CO on the right. And as you can see, there's not like a single morphology that describes each of these molecular lines, right? So we see, for example, that DCN appears to be pretty compact, while HCN, for example, is much more extended relative to the extent of the dust continuum. We even see very interesting sort of substructure in the outer disks. So we even see kind of like this secondary ring of sorts for H2CO, along with this sort of inner hole and outer ring for C2H. And this kind of like diversity of morphologies is actually similar to the diversity of morphologies we observe towards disks around solar type stars. So we're already seeing some interesting similarities, even just from this initial look. Now, when we take a single molecule and look at it across all the disks, we actually see similarities in the diversities, if that makes sense. So here we're showing C2H as observed towards all 5 disks. And for the 2 really well-resolved disks in the sample, we actually see the same sort of like either dips or holes in the C2H, and then these outer rings in the C2H emission. And that's similar to what was seen in this previous study in 2019, where they had a total of 3 low-mass M-star disks in their sample, also observed in C2H. And as you can see, you sort of see hints of this ring-like structure for 2 of the disks. I don't know what's happening with this 3rd disk here, but at least for 2 of the disks, we definitely see this ring-like structure. Okay. So we're already seeing some, sort of interesting connections to solar type disks and even to other low mass M stars, right? So moving forward, we want to try to answer 2 questions. The first is how does the sort of the chemistry in the outer disk regions, which is where our observations are most sensitive, or more sensitive to, how does that compare to chemistry in the inner disk regions, as has been explored by previous infrared chemistry surveys, which are sensitive to the inner disks. And then how does chemistry in our sort of low mass M star, our M4 to M5 disk sample, how does that compare to disks around solar type stars, which much of the spatially resolved disk chemistry studies have been focused on. Now, before we make these comparisons, let us justify that we can actually make these comparisons themselves by sort of putting our sample in context. Okay. So here's a plot showing the stellar mass along the x-axis versus the dust continuum flux for many disks. And I have highlighted in particular our sort of low mass M-star disk sample or M4 to M5 disk sample with these dark gold circles. And then in comparison, I've highlighted these white squares and white pluses, which are disks for which previous spatially resolved disk chemistry studies have been done. Okay? And in the background, I have sort of plotted a bunch of disks that were explored in previous studies that were focused on the dust continuum. So just, for the context. Right? And as you can see, our sample definitely fits within the brighter regime, for sure, the brighter regime of this overall trend, which means that, we certainly won't make any claims that our disks are, representative of the global M-star disk sample, but we can at least take this to be an initial view into the chemistry around these cool stars. Okay. Now, if we sort of extract these disks for which we have this, resolved disk chemistry information, we can sort of take this a step further and look more specifically at their gas. So now I'm showing the stellar mass along the x-axis versus C18O fluxes along the y-axis. Okay, and once again, our sample of these low mass M stars, of these M4 to M5 type stars, are shown with these dark gold circles, while we're comparing to solar type and Herbig A disks and with these white squares and white pluses respectively. And then in the background, there was some C18O data from lupus disks, so I've thrown those in for context. And as you can see, sort of all of these disks that have been, explored in these disk chemistry surveys do fall in this more gas-rich, bright regime, which, allows us to make this direct comparison, but do keep that in mind, that these are all sort of, particularly gas-rich. All of the conclusions we find are, due to the more brighter regimes of these spectrums. Okay. All right, so we put our sample in context, right? So yeah, the sample fits in quite nicely with these other disks that have been studied and spatially resolved in their chemistry. Yeah, so we've put the sample in context. We feel better about comparing them. So let's go ahead and make these comparisons. And to do that, we're going to investigate 3 different chemical benchmarks. So that's excitation conditions first. We'll take a look at flux ratios between different molecular lines. And then finally, we'll look at the disk average column densities for our entire sample. Okay, so let's start with excitation conditions after I drink some water. Okay. All right. So yeah, by excitation conditions, I mean excitation temperatures, column densities, and also optical depths. And we can actually estimate them for our most face-on or beautiful disk J1100 using this really cool methodology compiled by these sources. And we can do this for the C2H and HCN molecular lines, which both exhibit hyperfine structure. Okay, so I just want to kind of very cartoonishly go through this methodology here. So let's pretend that this series of lines that I drew in Microsoft PowerPoint represent some C2H line emission, okay? And as you can see, because it's data, it's a little noisy, it's not particularly pristine, right? Well, we can actually build a model of this line using these 4 parameters, where we've got some amplitude parameter, some optical depth parameter, some line width parameter, and then some sort of velocity offset parameter here. Okay? Now we pass our model, we pass our 4 parameters into MC, which is the MC powerhouse. And if you have not had a chance to use MC, you should, because it's awesome. Just to find an excuse to use it, it's great. So yeah, we pass these into MC, and we get back some, nice, pretty model of the data. So basically, we vary these parameters until we get a model that best represents our data. Very similar to what we did for Disc Jockey several slides back. Okay, and once we have the the parameters that best fit our data, we can actually use those directly in a series of equations to then measure the column densities, excitation temperatures, and optical depths. And that's exactly what we do for J1100 in terms of C2H and HCN. Okay, now I will say that we had sufficient signal to noise to estimate these values interior to the dust continuum. So these values do not apply for the entire disk, only to where we actually had signal to measure them. So that being said, interior to the dust continuum, we find that the C2H and HCN are both pretty cold, but HCN is slightly warmer. We find that HCN is more optically thick, and that C2H has higher column densities. And what's cool about this is that these excitation conditions are very similar, are very consistent with what has been discovered in a previous study for solar type disks. So, yeah. Okay, so the second thing we wanted to investigate were flux ratios between these different molecular lines. And we wanted to compare them to our low mass M-star samples, or our M4 to M5 disk sample, to solar type disks from these previous studies. And I want to highlight one result in particular, which is C2H versus HCN. So along the x-axis, I'm showing HCN fluxes, while the y-axis is showing a C2H line fluxes. And we're using the same sort of color scheme here, where these dark gold circles are the points from our work, so the low mass M-star, the M4 to M5 disks, and then the white squares and the white plus are the solar type and Herbig disks from the previous works. Okay, and as you can see, it's pretty remarkable, really. The trend that was sort of found or sort of suggested by even just the solar type and the Herbig disks actually extends quite nicely for our low mass M-star disks. Right? And we can take this sort of flux investigation a step further and compare flux ratios, or different flux ratios, as a function of stellar mass. So along each x-axis, I'm now showing stellar mass, right? And then each y-axis is the flux ratio, where the flux ratios are listed in either the bottom or the top of each plot. And again, using the same color scheme, where we have the dark circles are our M4 to M5 disks, and then the white points are the solar type and Herbig disks. And if you just let your eyes, just scan over these different plots, you see, well, there's not really much to say, right? All of these, each of these flux ratios don't seem to have much of a dependence on stellar mass, right? Now, these plots coupled with our previous plot suggest that there might be, there seem to be similar underlying patterns of chemistry, particularly in the outer disks where our sample, or where our observations are most, and where these measurements are most sensitive. Okay. Now, the very last thing that we're going to investigate, or the very last investigation that I will share with all of you, are the disk average column densities that we estimated across the entire sample. Okay. So here's a super fun plot, and I'm going to take a moment to explain it. So the x-axis corresponds to each of the 5 disks in our sample. The y-axis is the C2H versus HCN disk average column densities that we've estimated, assuming some assumptions, which are all listed to the bottom left. Basically, the stars are sort of assuming median values of excitation temperatures and column density, or not column densities, excitation temperatures and optical depths. While each of these rectangles, the gray rectangles, span 10 to 30 Kelvin in excitation temperature. The dark thin ones are assuming the thinnest optical depths, so like the lowest optical depths, while the pale thick rectangles are assuming the thickest or the largest optical depths. Okay. And lastly, this peachy gold horizontal line is the median estimate for this ratio taken from previous works using solar type and Herbig data, but mostly solar type disks, while the shaded region, the peachy shaded region, expands their 16th to 84th quartile estimates. Okay, so I explained all that to make one important point, which is that it appears that these our hydrocarbons, or like C2H, appears to be more enhanced relative to HCN for our, or at least even the median values are more enhanced than even the 84th quartile estimate found by these previous surveys containing these solar type disks. Right? And this enhancement in these low mass M-star disks is consistent with what has been found from studies of inner disk chemistry and previous infrared studies. Right? So this is a study done back in 2013, which compared C2H2 versus HCN fluxes and column densities for T-Tauri disks in black, and then the low mass M-star and brown dwarf disks in red. And as you can see in this flux plot, the values for the low mass M-star and brown dwarf disks are consistently much higher, or among the high scatter compared to these T-Tauri disks. Okay, now huge caveat. We have made a very critical assumption here that the C2H and HCN emission that we observe are both coming from similar layers in the outer disk regions that are sort of driving these measurements. So we do what we can with the data that we have, but that's a very important caveat, and it will be awesome if future studies with more sensitivity and higher resolution will be able to sort of tell us the behavior of C2H and HCN in these outer disk regions. Okay, so I threw a lot of words at you all, and quite fast based on how much time has passed. So give me a second to drink some water, and then we'll take a quick recap of what we've learned so far. Okay, so we started off this seminar with 3 main goals. The first goal was to just, sort of explore this sample of 5 important M5 or low mass M-star disks observed with ALMA, right? We were going to use this sample to dynamically estimate stellar masses for a subset, or as we were able to for these different disks. And then finally, we were going to survey the disk chemistry across the entire sample. Okay. Well, what did we find out? Well, quite a lot, even just from this small sample, right? So from our dynamical mass study, we saw that the sort of standard cell evolutionary models, tend to underpredict the dynamical mass measurements that we actually had, and that was pretty consistent in previous studies. Basically, we need more complex physics within these models to more accurately predict the dynamical masses. And we saw that stellar evolutionary models with star spots, which again serves as this kind of proxy for varying magnetic activity, we could actually use those to, once we interpolate those different tracks, to actually reproduce the dynamical mass measurements that we have made, which is awesome. And by looking at a pretty small collection of these low mass M-star disks, we were able to find that the stellar evolutionary models with star spots, when we took the optimal amount of star spot coverage we saw a very, very suggestive, tentative, possible downward trend in this optimal F spot with stellar effective temperature. But we really, really could use, future dynamical mass measurements of low massive star disks to really confirm or deny this trend over not only stellar effective temperature, but other stellar characteristics that we can use. Okay. And from our disk chemistry study, we found that there appear to be pretty similar patterns of chemistry that exist between our M4 to M5 disks, or low massive star disks, relative to solar type disks. But that there are suggestions that hydrocarbons might be enhanced across all of or across the inner and outer combined regions of low massive star disks relative to solar type disks, assuming that the C2H and HCN emission we observe is coming from at least similar layers in the disk. So again, we could really use future high resolution observations, and definitely of many more low massive stars, so we can really test these conclusions over a much more global population of these cool, young, cool M stars. And with that, I will, stop my talk and, oops. Thank you all so much for letting me come and speak at the seminar. It was a lot of fun. And yeah, I'll take any questions you may have. Thank you so much. Yeah, and also stop sharing because we just, there we go. Okay.
Thank you so much, Jamila. As a reminder, if you have a question, please use the raise hand feature under the participants tab, and we'll call on you and you can unmute yourself. If you are unable to unmute yourself, you can put a question in the chat and we will read it out loud. I see that we already have a question in the chat from Neil Turner, who says, thanks for the talk. Could you say more about the data you used to select the fiducial evolutionary models for the 3 stars with dynamical mass measurements?
Yeah, so by data, do you mean the models itself? We use the, for the fiducial ones, we use the MIS code from Choi et al. 2014, I think. Yeah, I think that's 2014. But if you meant, I guess, can you clarify what you meant by data? I don't know if I answered your question, but.
How did you choose the ages?
Yeah, so unfortunately, stellar ages for these really particularly young M stars is very uncertain. Actually have a, do you want to pull up? Yeah, basically, yeah, I can actually pull up a plot if you don't mind. Yeah, okay, let me just, which will kind of illustrate that we don't have a very good handle on on these ages. So okay, oh, go down there. Okay, yeah. So this is a really fun plot that is basically showing the fiducial stellar evolutionary tracks, where this kind of very lopsided grid, each of the vertical lines follows a different mass, while each of the horizontal lines follows a different age. So for example, if you follow this track with my mouse here, you can actually see the progression of a 0.5 solar mass star from 0.2 million years all the way down to 5 million years. And so this is where, these 3 dots are basically where our disks appear on this graph. And as you can see, because the lines are so vertical, you actually don't have a good constraint on which, like how old these stars are. So 1 to 3 million years, I mean, you can sort of guess, I guess, based on the star forming regions that these disks are coming from, but anything more precise is really difficult to say for these particularly young, for these particularly low mass stars. I don't know if that made sense, but yeah. Okay, cool.
All right, thank you. Next question is from Ilaria.
Hi, Jamila. Thank you.
Hello.
That was a very nice talk.
Oh, thank you.
I had actually a follow-up question on the one on Neil Turner. I was curious about actually the evolutionary models that you used. My experience is that the Baraf 2015 appeared to be among the best models for the low mass stars. And I was wondering if you have looked into those, and if so, what is the difference with the dynamical masses? Thank you.
That's a good question. So we were sort of using, we wanted to, we used the MIS models, and then we used what we could sort of pull from the Simon et al. 2019 compilation. So Do you know specifically what, I would love to look into this. Do you know specifically what the code name for the,
there is, I will send you an email, but Baraf 2015 has published the evolutionary tracks, and then you can interpolate given your luminosity and effective temperature. I'll follow up with you. Thank you.
Oh, thank you. Yeah, I don't know how different they are from the mist models that we had used, but and the spots models. But I'll investigate that. Thank you. Yeah.
All right. Next question is from Caitlin Crowder in the chat. She asks, for the dynamical mass study, is there a large enough sample of these low mass disks that could be probed with the current sensitivity and resolution?
Yes. So, I mean, they haven't been yet, but I think future work will be able to do that because, you know, we have ALMA and, you know, the awesome power of ALMA. So it's, yeah, it hasn't been done yet, but I think we definitely can. I don't know if that helps answer. It's like a very optimistic answer to your question, but yeah.
All right. Next question is from Heis.
Hi, Jamila. Nice talk. So you already mentioned larger sample sizes. So I was particularly wondering, are you thinking of extending the results to like lower and higher mass M dwarfs? Like, do you expect to see difference in the chemistry within the sample of M dwarfs, or are you just thinking of expanding the sample size to just get better number statistics, basically?
So both really. We don't really know what we're going to see because we would need to sort of expand our sample to really be able to investigate those much lower mass MSTAR disks. I mean, yeah. So we'll be able to expand and then really do a hopefully spatially resolved comparison between sort of our much more gas-rich disks that we've sort of tentatively started by exploring, and then in future, you know, we can sort of use that information to then motivate future observational samples that go much deeper and look at much, you know, maybe not as gas bright and, you know, not as massive disks, or disks are not as massive even in the low mass MSTAR regime. Yeah.
And do you think you can get all the way down to like the brown dwarf, or is there a limit, like these are the least massive stars you can do?
Well, because when you get down to brown dwarfs, the disks are so much smaller that it's, even with ALMA, unless you ask for very, very large amounts of time to observe, it becomes a little difficult to actually be able to resolve, you know, the chemistry within the disk rather than just seeing like, you know, an unresolved blob. So yeah, I'm not too sure if, you know, considering like a reasonable ALMA proposal with reasonable asks for time, if we would actually be able to successfully get a proposal to look as deeply as you would need to to see even those, you know, much smaller disks. So I don't know. I have to, yeah.
Okay, thank you.
All right. I have a question about the hydrocarbon chemistry.
Yes.
So one of your conclusions was when you looked at the ratio of the C2H to the HCN column densities, they were higher in your MSTAR disks than for disks around solar type stars.
Mm-hmm.
But when you plotted the flux of those two lines, it was like this really lovely trend that included the disks around the higher mass stars, and you also said that they had similar temperatures and optical depths. So I was wondering, like, if the fluxes and the optical depths and the temperatures are similar, why do you think there's an enhancement in the column densities?
Yeah, that's a good question. I guess I'll start by saying, you know, I guess the caveat that the values we've observed for the measurements we've gotten for the excitation conditions are only within the interior of the disk, right? So just to say that really quickly. And second of all, I guess even if you know, I guess actual like, deep chemists, correct me if I'm wrong, but you could still imagine, like, even if you're not getting the same amount of like flux, that you would still get a higher column density just because the even the like larger amount of molecules giving off less flux. It's like, I don't know if that makes sense, but maybe possibly, but where it's like we see, you know, we see the similar fluxes, yes, but the column densities are sort of going deeper than I guess the fluxes are going actually, right? Because fluxes doesn't always necessarily correlate directly to the abundances, so it's like not exactly the same relationship. But yeah, any chemist in the room could correct me if I'm wrong on understanding. Yeah.
All right. Do we have any final questions for Jamila? Yancy.
Yeah, how well behaved were your hyperfine fits, and did you run into any trouble? Was there any anomalous hyperfine structure or anything like that, or are they well fit?
Yeah, so great question. So, so one of the reasons that I showed the very kind of like wide constraints in that table before is because this process, even if you have really nice fits, which we did get pretty decent fits, you know, once you're like sort of, you know, you cut out the, what do you call it, the beam size, do beam dilution, and you sort of focus on that part of the disk where you're sort of right between the beam dilution and where the signal really drops off, right? But there are these intrinsic errors that you have to deal with. For example, even this like the underlying column density equation, for example, makes some assumptions on the shape of the line and treats it, I think, like Gaussian, and because it's not actually Gaussian, as you get to even, you know, these sort of higher optical depth values, you do sort of see kind of like this intrinsic breakdown of these equations, right? So yeah, these are all caveats I didn't get into here, but you sort of have to, even beyond the fact that our fits were pretty decent, you still have these like intrinsic errors that you see. So so the reason that that range was so broad, even for that I showed within that table, is because, you know, sort of like you do have these intrinsic errors that really don't come up when you use, you know, in CNC fits, if that makes sense. Yeah. But otherwise, you know, considering like the non-intrinsic, so like the CMC fits themselves, we do get pretty decent fits. I can actually show some if you're curious. Well, I guess if anyone else has any other questions, I can try to pull them up really quickly. I guess the nice thing about doing this over Zoom is that I can just kind of pull things from other parts of my computer without anyone knowing. Oh, okay. I think Zoom's actually kind of slowing down my computer. But if you email me while this is, oh gosh, okay. I think I might have broken my computer. Oh gosh. Okay. Well, feel free to email me and I'm happy to share results. Yeah, I tried to open a figure and now it's just, oh gosh, it's not opening on my computer. Sorry about that. Yeah, feel free to email me and I'm happy to talk more about that.
All right. Any final questions that will not kill Jamila's computer?
I have a question. I can raise hand because I'm a co-host. Yeah, just following up with Ilaria's suggestion, it's just a clarifying question. When we were asked about the ages, you showed the model. Did that model include spots or not?
The tracks that I chose.
The isochrones, yeah, to
right. No,
determine
that
the
was
age.
Yeah.
So the reason I mentioned is when we compare regular model with like a Baraf model, which is really great for M-stars. But then when we use like Fiden model that has magnetic field in it, the age difference could be factor 2 difference even, some depending on, yeah. Oh, wow. So you may want to compare the non-magnetic model and magnetic model together. So I was wondering whether your model had spots incorporated in it. So if you do, depending on the coverage of the spots, I think the age would change.
Yeah,
a little bit.
All right, thank you. Yeah, let me add that to my list of things to investigate. that would be great. I wonder. I mean, are the for the Baraf models, for example, I don't know if you know how off the top of your head how vertical even those sort of age tracks or isochrones are for those things. If not, I'll look into that. But yeah, very curious. Yeah, very curious to compare them. Thank you.
All right. I do not see any more questions, so I would like to invite everyone to unmute and thank our speaker for an excellent talk.
Thank you.
Thank you.
Well, thank you all for letting me come speak. It was pretty fun, so thank you. Okay.